Hey guys, Mr. Milton here. Today we're going to talk about concurrent lines. At the end of this video, you should be able to identify properties of perpendicular bisectors and angle bisectors, and you should be able to identify properties of medians and altitudes of a triangle. Okay, we're going to start with some vocabulary words. Concurrent lines. So concurrent lines are three or more lines that meet in one point. Okay, the point of concurrency is the point at which the concurrent lines meet. Okay, so if three lines meet at one point, they are concurrent. That point that they meet at is called the point of concurrency. And in this lesson, we'll look at the different points of concurrency. So, first, let's look at a circumscribed circle. A circle is circumscribed about a polygon or around. You can see both of those. A polygon when the vertices of the polygon are on the circle. So here you have S, Q, R in this circumscribed circle. Circumscribed. Okay. All right, and if you notice that we have three lines that meet at one point, this line, this line, this line, they all meet at one point. That point is called the circumcenter. Okay, a circumscribed circle. That the center of that circumscribed circle will be the circumcenter. Again, notice that the circumcenter of a triangle is the point of congruency, so the place where all three of those perpendicular bisectors meet in a triangle. Okay, a circle is inscribed in a polygon if the sides of the polygon are tangent to the circle. So here we have tangent line connecting, that would make a 90. Well, we'll see that. We'll talk about that. So this is an inscribed circle. This circle touches the sides of the triangle just once. Okay. And inside the inscribed circle, or the center of the inscribed circle, is called the incenter. Okay, notice that that is a point where three lines meet. We have this line here, this line here, this line here. They all meet at that center. And these lines, if you can tell by the markings, are angle bisectors. So, the incenter of a triangle is the point of concurrency of the angle bisectors of the triangle. Okay. All right, a median of a triangle is a segment that has as its endpoints a vertex of the triangle and the midpoint of the opposite side. So notice here we have a median drawn in this diagram at the bottom. We can tell that this is a median because vertex to midpoint. We can tell this is a midpoint because they give us the markings that those two sides are congruent. Okay. The centroid of a triangle is the point of intersection of the medians of the triangle. The centroid is also known as the center of gravity. All right, so we looked at three points of concurrencies, also known as centers of triangles. So there's three different centers of triangles. Well, yeah. So let's talk about some of their special features. So not only are they circumscribed or circumcenter. The circumcenter of a triangle has some special properties. The perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. Okay, notice that the circumcenter is made up of perpendicular bisectors, and so when we talked about perpendicular bisectors last section, we said that if a point was on a perpendicular bisector, it was equidistant from the endpoints of the segment it bisects. So, because we have three perpendicular bisectors that meet at one point, okay, that means that all three of the sides are being perpendicularly bisected. This is on the perpendicular bisector of all sides. So it is equidistant from all the endpoints. Alright? For the end center of a triangle, the bisectors of the angles of a triangle are concurrent at a point equidistant from the sides. So for our end center, this point created by the angle bisectors is equidistant from the sides. And remember, when we talk about equidistant, we're talking about a perpendicular distance, a straight line to the sides. So there we've looked at two properties, or the properties of two centers of triangles up there. One created by the perpendicular bisectors, one created by the angle bisectors. Alright? Okay. An altitude of a triangle is the perpendicular line from a vertex to the line containing the opposite side. Okay, to the line containing the opposite side. So in an acute triangle, the altitude is inside. On a right triangle, the altitude is on the triangle. Notice that this is the altitude here. And in an obtuse triangle, the altitude is actually outside. Okay, so we have our triangle here. Our altitude is the line that contains it, is perpendicular to the line that contains it. Okay, so it's outside the triangle. Okay, these lines also have a point of concurrency, and that is called the orthocenter. Okay, the orthocenter of a triangle is the point of intersection of the lines containing the altitudes of the triangle. Alright, so talked about end-center a little bit more in depth. We've talked about circumcenter a little bit more in depth. We're going to talk about the centroid a little bit more in depth. Okay, so the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. Okay, so this is how it goes. From vertex to centroid is 2/3 of the line. From vertex to centroid is 2/3 of the line. So DC is 2/3 of the line DJ. EC is 2/3 of the line EG. FC, vertex to centroid, is 2/3 the distance or the length of FH. Okay, another way to say this is the distance from the vertex to the centroid is twice the distance from the midpoint to the centroid. Alright. Okay, And for the orthocenter, there's nothing really special about the measurements, but we can say that the lines that contain the altitudes of a triangle are concurrent. Okay, there's no measurements or anything to it that we can that's been found to have a relationship, but they do meet at one point, called the orthocenter. All right, so revisiting centroids a little bit. It says in triangle ABC, DE is 6. Label that. AH is 11. AH is 11. Sweet. Okay. So they want us to find the length of each. They want us to find BD. So as we look at BD, first of all, we notice that these are all vertex to midpoints. Vertex to midpoints, so these are all medians. And so we have a centroid given to us at D. We know from our centroid theorem that from the vertex to the centroid is 2/3 of the line, and from the centroid to the side is 1/3 of the line. Okay, so they want us to find BD. We know from DE it's 6, so this is 1/3 of the line. This should be 2/3 of the line. Again, another way to say this is that BD is twice as long as DE, so BD should be 12. BE, they want us to find. Well, we've already found BD. We have DE. That means BE must just be the sum of these two, 18. BH, well, they told us that AH was 11, so BH must also be 11, since H is the midpoint from C to the midpoint. And then AB, well, 11 plus 11, 22. They have all those values. All right. Try to give number 2 a try before I go through it. You can pause it here so that you can do that. Try to use a different color. All right, so in triangle WOR, they told us that WM is 16. It's here to here. That RZ is 18. This whole line, 18. Okay, and they want us to find the lengths of each of these. So, MX. Well, they told us that WM was 16. Again, we know this is twice as long as the other side because this vertex is centroid. So since this is 16, this must be half as long, 8. MX is 8. WX is the sum of those two then, which is 24. MZ, well, they told us that this whole thing is 18. So MZ is from the center to, or from the centroid to the midpoint, and so that's 1/3 of the line. 1/3 of 18, 6. So MZ must be 6, and then MR is the rest of that, or we could say 2/3 of 18 is MR, which is 12. All right, so there we go. There's centroid, center of gravity, finding those values with the 2/3 ratio. Sweet. All right. So we talked about different lines, and now we're going to practice a little bit identifying them. So over here it says name each figure in triangle BDF. We want to name an angle bisector. Okay. Try to give this a shot, do this, and then come back to the video, or pause it and come back to the video and see how you did. So for number 3, an angle bisector, looking at our diagram here, we see our bisecting line. So an angle bisector is that line BE. I can call it ray BE, that's what I'll do. Okay. Okay. A median, remember, goes from the vertex to the midpoint of the opposite side. So we look at our triangle BDF, where's B? PF. Okay, so it's a big triangle here. From F to C, vertex to midpoint of the opposite side, FC is a median. Okay, notice that AC is not a median because it does not go from the vertex. Okay, perpendicular bisector, perpendicular makes a 90-degree angle, bisector cuts it in half. There we have AC because we have a right angle. We have that it goes through C, which is the midpoint. And so AC. Looks like raised CA maybe, but I'll just call it AC. Okay, and then an altitude goes from vertex perpendicular to the other side. Let's see where that will be. Gotcha. So here we have D. See a 90-degree angle here. So from DG must be an altitude. All right. So there we have it. Those are our figures from triangle BDF. All right. So now we're doing that kind of backwards here. It says identify each as perpendicular bisector, an angle bisector, a median, or an altitude. It is possible to be more than one. So looking at number 7, they ask us about ST. Well, ST in this figure, 90 degrees from the vertex, so it is an altitude. So it's definitely an altitude. Does it go to the midpoint? No. Okay. Does it perpendicularly bisect this line? No. Perpendicular but not bisect. So that's just an altitude. UW goes from vertex to midpoint because of the markings there, so we know it's a median. No 90-degree angles or anything like that, so that's all that it is. Number 9, BD. BD is definitely an angle bisector. Angle bisector. You would probably be tempted to call it a median, but remember that they have not told us that those are congruent. So since they didn't tell us that those are congruent, we can't call that a median. Okay, and it's not an altitude because it doesn't go 90 degrees. Line N is a perpendicular bisector, 90 degrees. I'll call it perpendicular bisector to save some ink and time. MY is a median. Okay. And it's just a median, doesn't bisect any angles, doesn't look like it is perpendicular to that side, doesn't tell us that's perpendicular to that side, sorry. And then KX is an altitude because it goes from the vertex to the opposite side, but it's also a perpendicular bisector because it 90 degrees and cuts it in half. And since it goes from the vertex and cuts it in half, it must also be a median. Okay. All right, so there we have it. Okay, now some applications to the triangle centers. Finish this off. All right, it says city planners want to locate a fountain equidistant from 3 straight roads that enclose a park. How can they find the location? So they're basically asking us, hey, which center do we want to use? It's a multiple choice question in the sense that we have the circumcenter, we have the incenter, we have the centroid, and we have the orthocenter. Now this gets a little bit easier because remember the orthocenter really doesn't have an application that we can use a whole lot. It's just cool that all the altitudes meet at one spot. But as far as finding it for an application, we won't have it. Okay, so we want to find a point in here that's equidistant from the sides or the streets, which is like the sides. Okay, this point is going to be the incenter. Okay, it says the towns of Adamsville, Brooksville, and Cartersville want to build a library that is equidistant from the three towns. Where should they build the library? So here we go. We have these three towns. These three towns on the map. Okay, want to be equidistant from these three towns. Where do we want to build it so that it's equidistant from those three towns? Well, we want to build it somewhere where it's equidistant to the vertices. Which center is equidistant to the vertices? A circumcenter. A small park has 3 pieces of playground equipment, a slide, a swing set, and monkey bars. Families have collected money to install a water fountain. Parents want the fountain to be equidistant from each piece of equipment. How could they find a spot? Very similar to the last question. We have 3 points that we want to be equidistant from. That's going to be, again, the circumcenter. Circumcenter. And finally, it says, suppose you want to hang a model airplane from the ceiling so they stay upright horizontally. You want to find the point at which to hang the triangular shaped stealth bomber model. For this shape, where would it need to hang? So here we go, the stealth bomber model here. We want it to hang so that it doesn't lean left or right, front or back. We want the center of gravity. So the center of gravity is called the centroid. Alright, so we've looked at the lines that make up the points of concurrency. Those special points gave their names and their characteristics, and now we've applied them, identified the lines. So make sure that you have that. If you need to rewatch this video to do that, to remember that, do that, but also make sure you're studying and making sure you can tell the difference between a median and an altitude, an angle bisector, a perpendicular bisector, and all those lines to make that a little bit easier. All right, see ya.